Okay, so let's go ahead and do right triangle trigonometry. So, when we're doing right triangle trigonometry, the first thing we start with is generally, well, a right triangle. And so, second. There you go. So we start with a right triangle, like so. It doesn't really have to be perfect. It's just supposed to be a sketch. So if I tell you that these are supposed to be straight lines, then just take my word for it. So we start with a right angle here, and we start with, let's say, an angle theta here. So this is the Greek letter theta, and that's what we use to denote an angle in a right triangle that is not the main right angle. Now, let's go over the side name. So when you have this angle theta, the longest side of the right triangle is going to be the side opposite of the right angle. That's what we call the hypotenuse. One second. Okay, so that is the hypotenuse. So that's the hypotenuse. The angle right next to the angle theta is called the adjacent because it's right next to it. And the angle to the opposite of the theta is, of course, called the opposite. So you have the opposite, the adjacent, and the hypotenuse. And so the three things we care about are what we call the sine of theta, the sine, sine of theta, which we denote as sin of theta, like this, the cosine of theta, which we just write cos theta, and the tan of theta, or the tangent of theta, right here. And so things are sine, cosine, and tangent. So I have sine, cosine, and tangent. And so the common way to remember these is with a mnemonic called SOH, TOA. And this mnemonic will probably help you remember things a lot better. So SOH stands for sine is equal to opposite one second. Opposite over hypotenuse. So opposite over hypotenuse. Ka stands for cosine is equal to adjacent over hypotenuse. Adjacent over hypotenuse. And TOA stands for tan is equal to opposite over adjacent. And so the ratio of opposite to adjacent is equal to tan. The ratio of adjacent to hypotenuse is equal to cosine of theta. And the ratio of opposite to hypotenuse is equal to sine of theta. And so if I were to give you, let's go ahead and say a triangle like, let's do this. So I give you a triangle like that and say that this is a right triangle, that this is our angle theta, and let's go ahead and say that I gave you that our sine, or sorry, that our not our sine, that our opposite was 1, our adjacent was 3, and our hypotenuse was 2, or sorry, that doesn't make sense. So our opposite is 1. Our adjacent is, let's see. Let's go ahead and say that our adjacent is, let's go ahead and say it's 3, just 3. And so the few things I want you to do are, first, what is sine of theta? What is cosine of theta? And what is tangent of theta, or tan of theta? What are these 3 things? And so, for sine and cosine, might be a bit confused, but for tangent, you would go, okay, we have theta, so we can look at the opposite, 1, and the adjacent, 3, and say that tan of theta is equal to 1/3. Now, for sine and cosine, well, we know the opposite and adjacent, but we don't know the hypotenuse just yet. And so, what we would use is something we call the Pythagorean theorem. So what is the Pythagorean theorem? Well, it essentially states that in a right triangle, so one that looks like, let's say this, right triangle like this, it doesn't really matter what the sides are, but, or what the specific lengths of the sides are, so long as we have 2 sides and 2 legs, you would say, of the right triangle, and 1 hypotenuse, where the hypotenuse is c, then the length of c squared, the length of c times itself is equal to a squared, the length of a times itself, plus b squared, the length of b times itself, which in practice means that c is equal to the square root of a squared plus b squared. This is called the Pythagorean theorem and is very, very useful in right triangle trigonometry and in certain ways also in unit circle trigonometry. And so, in this case, let's go back to this triangle, right? Let's go back to this triangle right here. We have a right triangle where one of the legs has a length of 1 and the other leg has a length of 3. And so, what would the length of this leg be? Well, it's not going to be a very nice number, but it is going to be something that we can write if we use this square root sign. And so, let's do Pythagorean theorem. So, length of c is equal to the square root of 1 squared, or 1 times itself is 1, plus what is 3 times 3. Well, that would be 9, and so this is the square root of 1 plus 9 is equal to square root of 10. So, so this is the length of our hypotenuse. Now, depending on who you ask, you might just write this as, well, 1 second. Depending on who you ask, you might just say this is square root of 10, but oftentimes mathematicians will abbreviate it and just say this is root 10. So the length of our hypotenuse is root 10, and therefore sine of theta is equal to the adjacent, or sorry, is equal to the opposite over the hypotenuse, and so it is equal to 1 over root 10. And cosine theta is equal to the adjacent over the hypotenuse, and in this case the adjacent is 3 and the hypotenuse is root 10, so that's 3 over root 10. Now one very cool thing to note here. So if we want to know, if we, let's say, knew the hypotenuse length, but we didn't know the length of the adjacent, or the length of the opposite or the adjacent, then what we could do is we can say, hey, wait a second. If we can figure out the cosine of the angle, then we can figure out the side. How do we do that? Well, let's go back to these equations. We have cosine is equal to adjacent over hypotenuse, so we can say that hypotenuse times cosine theta is equal to adjacent. And we can do the same thing here. We can multiply both sides of this equation by hypotenuse and get that hypotenuse times sine of theta is equal to opposite. And so those are actually two very useful equations. And those are two very useful equations because sometimes you'll be dealing with triangles where you know the angles, you know the length of the hypotenuse, and it'll be really, really easy to just think of this side length as being the hypotenuse times the cosine of the angle, or the sine of the angle, etc. Now, there is one last thing that I really should mention that any older math teachers will absolutely hate me for not mentioning, and that is, let's go ahead and clear this whole board. A second. So let's go ahead and clear the board, and that is, remember that we said that cosine of theta in that right triangle is equal to 3 over root 10, and that sine of theta equal to 1 over root 10. Well, a lot of people really do not like having these square roots in the denominator of a fraction. And so the reason why is because back when we didn't have as fancy calculators to actually calculate square roots, we basically just had to look up numbers in a table, and we would have to find the decimal number, like which would be which for root 10 using a calculator would be about so root 10 is equal to about 3.1623. So root 10 is equal to approximately that. That is the type of information that people may have been able to find back in the day when they used like lookup tables for the stuff like this instead of calculators. And so the problem is that when you're dividing by a number like 3.1623, it's really awkward and weird and kind of hard to do. And so what people generally prefer doing is multiplying by these weird long numbers. And so what people did is what we call rationalizing the denominator. So to do that, people said, well, let's multiply this by a funky form of 1, a weird form of 1, and that is square root of 10 over square root of 10. And why are we doing this? Well, because what is square root of 10 times square root of 10? By definition, the square root of 10 is a number that, when you multiply it by itself, is equal to 10. And so this means that 3 over 3 divided by root 10 is equal to 3 times root 10, or just 3 root 10, over 10. And this 3 root 10 over 10 is the fraction with a rationalized denominator. I'm just going to type that out. Rationalized denominator. And then you would want to, in general, rationalize the fraction. So that's something that is so that's something that a lot of people might get a little bit annoyed at you if you don't do. Nowadays, because we have more advanced calculators and stuff, we don't actually need to worry too much about rationalizing the denominator, especially because sometimes it's easier to work with fractions when they're written like this. But nowadays, as you know, to sort of remember old tradition, and also because a lot of people are just used to it, we often rationalize the denominator anyway. So if we want to write 3 over root 10 is equal to cos theta, we would actually rationalize the denominator by multiplying by whatever was in the denominator to square it, and then get 3 times root 10 over 10 is equal to cosine theta. So we could do the same thing for sine theta. How do we rationalize this? Well, we want to get a normal number in the denominator, and so we would multiply by root 10, because root 10 times root 10 is equal to 10. And so we get, and because we don't want to change the value, we would multiply it by root 10 over root 10, which is, again, just a strange form of 1. So this becomes root 10 over 10 is equal to sine theta. And so, yeah, so something like this, it's a lot easier to actually work out with a calculator if you only know the value of root 10 and nothing else. But if you're using a modern calculator, where you can just input 3 divided by root 10, then it works the same either way.